Okay, so we are looking at section 6.4, exponential functions. Y'all are familiar with E. That's not a big deal, but the logarithmic differentiation is going to be the difference here. Okay, objectives. We want to review our properties of y equals e to the x and y equals natural log x. And then we want to differentiate exponential functions by first taking the natural log of both sides. That's going to be a little bit different right there. Okay, so here is your definition of E. We've talked about what E is before, but you did not know how or what to do with it. So we're looking at this, and you have limit as n goes to 0 of 1 over n, or 1 plus n to the 1 over n, or you can do limit as n goes to infinity of 1 plus 1 over n to the n. Okay, notice your 1 over n and n's trade places there, and so therefore it makes a difference whether it goes to 0 or to infinity. But either one of those definitions give you your 2.718 that we know. Okay, I am sure that you remember that e to the x and y equals natural log x are inverses of each other. So therefore, if you take the natural log of e to the x, it equals x, and the e to the natural log x equals x. It's really important that you watch for this, because a lot of times on AP exams they give you problems like this one down here where things look complicated, but they're really not. You start looking at it, you're supposed to take the derivative, and you're thinking, okay, negative sign, and then by the chain rule I have to do 1 over, and over. You got multiple steps here, but if you'll recognize that you've got that natural log of e, then you know that y becomes just cosine of 7x, and so therefore your dy dx, or y prime if you wrote that, would just be a negative 7 sine 7x. So nice, easy, not a big deal if you do it like that. Okay, let's look at a couple other things here. General exponential function we know is y equals b to the x. That's not a natural or anything like that. That's just your general one when you've got b to the x. So then your definition is b to the x equals e to the x natural log b. We've talked about this before, but it's always kind of tough for people to understand and to remember. I do want you to remember that right here, the x that's in the front can also be written, sorry, not writing too well today, natural log like that, and the x comes up as an exponent, and so therefore you can see your e's to the natural log, that those would cancel out, and that gives you your b to the x. So that's a more common way that you might recognize it than looking at it like it is typed above, but you need to be able to recognize it either way. Derivative and integral properties on this, if you've got the derivative of b to the x, I hope you remember that that's b to the x natural log b. I think most of you do. And then the integral of b to the u du is b to the u over natural log b, because you've got to offset this that showed up right here. You've got to offset it down here if you're integrating back. And then, of course, plus c. Well, I've got this question down here. Does this still work for e to the x? Yes, it does. Because if I take the derivative of e to the x, following these little natural log rules right here, or excuse me, these general exponential derivative rules right here, then that would be e to the x natural log of e. Well, but natural log of e is 1, and so e to the x times 1, that's still going to give you e to the x. And we know that our derivative of e to the x is e to the x. Okay, well, what if I integrate? If I integrate e to the x dx, then following my second rule that's right here, that would give me e to the x over natural log e. Well, natural log e, of course, plus c, sorry. Natural log e is 1. We just said that. So again, we get e to the x plus c. And we know that that's what we're supposed to get when we integrate e to the x. So rules still apply even if it's an e, 2.718 for the base instead of a whole number that you're looking at. But same concept no matter what. Okay, now then let's look at the next thing. We want to figure out why it is. We know this. We know that if we take the derivative of 8 to the x, that we get 8 to the x natural log 8. And we know about this integral over here. Those were given to us on the page before, and we've worked with them before. But why? Why does that happen? Okay, I want us to go back to your little rule that we had written down on the page before. B to the x equals natural log b, or e to the x natural log b. Okay. All right. Well, in this case, then, I'm looking at 8 to the x power, and it's going to equal e to the x natural log b. And that makes perfectly, or natural log 8, excuse me. That makes perfectly logical sense if you raise that x up like we did on the other one, and then you've got e to the natural log, so you get 8 to the x equals a to the x. But now then, let's take our derivative so that we can come up with both sides. So I'm going to take the derivative with respect to x of 8 to the x, and that's going to equal the derivative with respect to x, taking the derivative of both sides, of e to the x natural log 8. Now remember, when you see this, natural log 8 is just a constant. Okay, it's not a variable up there. So when I still have over here on the left the derivative of 8 to the x with respect to x, on the right hand side I know that the derivative of e to the x is e to the x, and then by the chain rule I've got to take the derivative of this constant, or the derivative of the constant that's in front of x, so we get natural log 8. Okay, well, we've already said that e to the x natural log 8 is 8 to the x, and so that is your proof of your other of this property right here. Woo, sorry y'all. And yes, it's gone, but y'all are used to seeing that now that you worked with this tablet. Okay, on this other one over here, instead of taking a derivative, I want to integrate. All right, so that means I am integrating 8 to the x dx. That is going to be the integral of e to the x natural log 8 dx. Okay, well, when I integrate that, integral of e to the x is e to the x, and then I have to offset the constant, so 1 over natural log 8 equals sorry, not sure why I have equals there, 1 over natural log 8, e to the x natural log 8 plus c. And so therefore that is going to give you your 1 over natural log 8 times 8 to the x plus c. And so there's your property. So that's exactly what we had. That's what we developed. We're doing good. Okay, let's do something a little bit easier, and this is really pretty cool. Remember that whatever you're doing to one side, you can do to the other side. So let's do that on this one. I've got y equals 8 to the x, so let's take the natural log of both sides. Whoops, there went my pen. Natural log y equals natural log of 8 to the x. I'm taking the natural log of both sides. This is going to be, it's going to lead us into logarithmic differentiation. It's really nice, and it really helps on lots of problems to make them easier. All right, so if I take then the derivative over here of natural log y, that's going to equal the derivative over here, and I'm going to move that x that was the x one, I'm going to move it out in front, x natural log 8. Okay, so again, really nice thing here, derivative of natural log y, 1 over y, and then I'm hoping to goodness y'all are remembering implicit dy dx, right? Equals, and over here, my derivative of this, derivative of x, is just going to be the constant that's with it, and so that's natural log 8. So then that means, moving up over here, that dy dx is y times natural log 8. And look at that. Y was originally 8 to the x. And so there is a much nicer way of taking that derivative. So very nice. All right, one more. I'm going to let y'all try it. Remember that f of x was the same thing as y, and so I want to let y'all try that one, and then we'll work it out in class and double check to make sure that you have the right answer. Okay, so y'all try that one. Come back, join me on the next page, and that'll be the last thing that we'll do. Okay, so here is our final problem. Another example of logarithmic differentiation. If you do not do this one with logs, look at what all you have. You've got the quotient rule, and you've got chain rule, and you've got, I mean, all kinds of stuff going on here, and it's ugly. It is not fun. But if you can remember to take the natural log and simplify this, then this becomes not a bad problem at all. So my f of x, I'm going to think of as a y. So this is going to become natural log y. Well, I'll just write it all as one word there, natural log y, equals. Now then, we want to use all of our properties here. Okay, I'm going to go ahead and write this, but I want you to be thinking about what that means. That means I've got the 3x plus 7 to the 5th all over my cubed root of x plus 2. See, that right-hand side has all that stuff going on, but when you use natural logs, it expands so nicely. So you have natural log, and then that would be 5 in front of it, 3x plus 7, minus, and then a 1/3 natural log of x plus 2. So really nice to expand it out like that, and then just take your derivative. So my derivative of natural log y, of course, is 1 over y. dy dx, we have no idea how to get rid of these little boxes that show up randomly, equals, when I do this, derivative of natural log is going to be 1 over this 3x plus 7. So I'm going to have 5 over the 3x plus 7. And then by the chain rule, the derivative of 3x plus 7 is a 3, so times 3, but that's not a big deal. We'll deal with that. Minus, okay. Now then I'm going to go ahead and do this as 1/3 times 1 over x plus 2. Derivative of x plus 2 is just 1, so it's good at that point. So simplifying just a little bit more, I have dy dx is going to equal y times 5 times 3 is going to give me a 15 over 3x plus 7 minus 1 over, and you can distribute or you can leave it, 3x plus 6. Okay, now remember I can't leave that y right there, so I'm going to plug back in. I'm going to go back up to the top and plug that in. My y was 3x plus 7 to the 5th all over the cubed root of x plus 2 times my nice little bracket from above, 15 over 3x plus 7 minus 1 over 3x plus 6. And we are now in great shape. There is our derivative, and we're good to go. So finishing last thing, maybe, there's homework, and I will talk to y'all tomorrow. Bye.